Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we are going to solve group permutations of palindromes. The prompt states, write a function that takes an array of strings as the input and returns an array of arrays where the subarrays in the result are all permutations of the same palindrome. So for example, these three strings are all permutations of the palindrome race car, so we group those. Then these two strings are permutations of the palindrome ANA. These three strings here don't form a palindrome with any permutation of their characters. And finally, BOB is the last result and the only permutation of this palindrome. So just to refresh ourselves, a permutation is a different ordering of a string's characters. For example, the word dev, D-E-V, has 6 permutations. So we can rearrange those characters 6 different ways. A palindrome is a sequence of characters that is the same forward as it is backwards. So pop, P-O-P, would also be pop backwards. The same for level in both ways, race car both ways, and even the phrase never odd or even. If you ignore casing and spaces, it's the same characters forward and backward. So let's discuss what it means to group permutations of palindromes. A string is a permutation of a palindrome if you can rearrange those characters in some order that will form a palindrome. So this string here isn't a palindrome, but a permutation of it is. So that means if we rearrange the characters, it can form the palindrome race car. And then the same with this string. If we rearrange the characters or form another permutation of it, we can also form the palindrome race car. And then again, these two strings are permutations of different palindromes. So when we say a string is a permutation of a palindrome, we just want to know if we can rearrange those characters in any order to form a palindrome. And then if a string cannot form a palindrome with any permutation, then we simply leave it out of the solution. And then strings that can form the same palindrome, their permutations of the same palindrome, should be grouped together, like race car. So they're permutations of the same palindrome, they can form a palindrome, and this also means they're simply permutations of each other. So after walking through that, we can really see there are 2 steps to solving this problem. First, we just need to determine if a string is a permutation of a palindrome. And then if it is a permutation of a palindrome, we include it in our solution output, and we want to group it with other permutations of the same palindrome, which means these strings are simply permutations of each other. Let's first think through how we'll determine if a string is a permutation of a palindrome. So we know race car is a palindrome, and the standard way to check if a string is a palindrome is start at each end, and then check if each character is the same on the other side until you reach the middle. So we start at the front and the back, and we see they're both are, so we continue. We move in by 1 character on each side, we see they match again, so we continue. We move in again and see they match, so we continue. And finally, we reach the middle, and it's only 1 character, so we're done, and we know this string is a palindrome. So if we looked at the middle character, or the middle slot if there were 2 characters in the middle, we know that to the left and to the right, they're going to be mirror images of each other. This is how we know a string is the same forward and backward. So this works for a normal palindrome, but what if the string is a permutation of a palindrome? So this string here has the same characters as race car, so it's the permutation of a palindrome, but at the moment it's not arranged as a palindrome, so we can't use the standard test with it. So the brute force way to approach this would be to just take this string and form every permutation of it, and then check if that permutation is a palindrome. This is incredibly inefficient because it's going to take O of C factorial time. This is a very, very bad time complexity, and in fact, it's one of the worst. Really, the only benefit to this approach is that we still only use constant space. However, factorial time is unacceptable. We would use C factorial time to generate all the permutations, and then a linear O of C time to walk through and check if it's a palindrome. We know this isn't acceptable, so how can we optimize it? Well, one thing to note is that we don't care what palindrome this string can form. We want any permutation that can form any palindrome. So it's possible a string can actually form many palindromes, but all we want to know is, can it form one? Is any arrangement of these characters going to be a palindrome? So for some intuition, let's take some permutations of the race car palindrome. Instead of trying to rearrange them to form a palindrome, let's see what characteristics they have in common that are shared between all the permutations that we can use to determine if it can form a palindrome. So if a string is the same forward as it is backwards, like with race car, we know characters must repeat. In fact, when we did our walk from the front and the back, we were checking if every character had a corresponding match, because a palindrome must be a mirror image on the left and right side. So this means there's actually going to be the same characters on both sides, or there's going to be twice as many characters as one side. So if we look to the left, we have these characters, so that must mean those exact same characters must be on the right. So we're going to have twice the number of characters as half the string. That's how we know it's a palindrome. So we're not actually trying to see what palindrome it can form, we just want to know if these characters can form a palindrome, and we can check this by counting the characters in a string. So we have this race car palindrome here, and then we have a permutation of it. We see there are 2 A characters, 2 C characters, 1 E character, and 2 R characters. We know that anything multiplied by 2 is an even number. So if there's 1 A on each side, as we see here, there's going to be 2 total. If there's 2 characters on each side, that would make 4 total. 3 on each side, that's 6. So anytime we multiply something by 2, it's going to form an even number. So this actually leads us to our definition. If the count of each character in the string is even, it's going to be able to form a palindrome. But then you're probably looking at this E and thinking that can't be true. So we can actually have one character that has an odd number. If there are an odd number of characters in the string itself, that means it's possible to have one middle character. So it's still possible to form a palindrome if you have an odd number of characters, because this middle character still allows it to be the same forward as it is backwards. So we can have one character that appears an odd number of times, but the rest must be even, and then this is how we know it can form a palindrome. Let's take a little bit more extreme example just to prove this to ourselves. So we see here we've just increased the number of characters on each side of the midpoint. There are 3 R's on one side, and then a matching 3 R's on the other. So when we double that, the 3 on a half, that forms 6. We still have 2 C's and 2 A's, so those are even numbers as well. Then we see the E appears 3 times. Well, there's an E on each half, and then our middle E. So with this middle character, we can still have one character's count that appears an odd number of times. So we see that's the secret to checking if a string is a permutation of a palindrome. All we have to do is count the number of characters in a string and make sure they all appear an even number of times. And then we can have one character that appears an odd number of times. With this, we know this string can form a permutation of a palindrome. We see that in reality, it could form many different palindromes, but all we care about is the fact that it could form any palindrome. It could form at least one palindrome, and we know that with the character counts. So then the question is, how do we store these character counts? And to do this, we can use a hash table. We're going to add a data structure where the keys are the characters in the string, and then the values will just be the count of each. And we're actually still only going to use constant space because at most, if we're using the English alphabet, this hash table can contain 26 characters. So the hash table is what's going to allow us to track this count. And then we'll iterate through the count of each character, and if we see that they're all even, or all are even but one, then we know that this string could form a palindrome with at least one of its permutations. So now we've solved one of the steps. We know how to determine if a string is a permutation of a palindrome by counting its characters. And now let's determine how we can group strings that are permutations of the same palindrome, which also means they're permutations of each other. So we want to combine these strings into subgroups for the solution. So we have all these permutations of race car, and we want to know how we can recognize that they should be grouped together. Well, we were already calculating the count, so then another thought is that we just compare the count each time and can add those strings together. But this is going to be O of C squared to make all these comparisons, because this would require comparing characters in nested loops. So then what if we instead sorted the strings? If we sort the strings, we can take the sorted version as the key to a hash table, and then the value is going to be the array of the unsorted string, so this will allow us to group the ones in their original order, but by sorting it, we know that they must be grouped together. So strings that are permutations of each other, that means they have all the same characters. So if we sort their characters, they're going to form the exact same sorted string. So we can use this sorted string as the key, and then store the unsorted version in an array for the value. Then we can simply return this array in the solution output. And that's all we need to do to group them. So with that, let's walk through all the steps to the solution. We're going to begin by just iterating through all the items from the input. Then we're going to check if a string is a permutation of a palindrome by counting all the characters in the string. If all the counts are even, or only one count is odd, we know this string could form some palindrome. We don't know or care what this palindrome or the palindromes are, we just know it could form at least one, and this means it can be included in the solution output. Then to group the permutations together that are permutations of each other, we just sort the string and use a hash table where this sorted string is the key, and then we use an array to group all the similar permutations. The time complexity on this is n times c log c, where c is the number of characters in the string, and n is the total number of strings. So we're just assuming c as the count for a worst-case string scenario. So we iterate through all the strings, and we must sort them to add them to our solution output. The space required for this is n times c, where n is the total number of items, and c is the characters. So notice we're accounting for the items and the characters in the strings for both the time and the space. This is because the number of items can grow arbitrarily large, and then also the number of characters in an individual string, so we must account for both. And now we're ready to write the solution function group permutations of palindromes. We're going to store the permutations of palindromes in a hash table, where the key is the sorted string of all the permutations, and the value is an array of all the matching strings. Then we iterate through all the strings from the input, The first thing we're going to do is check if the string is a permutation of a palindrome. So let's write a function to do that. We initialize the function. We're going to determine if a string can form a palindrome with any permutation of its characters by counting the characters in the string. So we initialize a character count table where the key is going to be each character and the value is going to be the count of each character in the string. We're going to iterate through each character of the string. First, we check if the character exists in the table yet, and if it doesn't, we need to initialize it. So we add it to the hash table and set its value to 0. And then every loop, we're going to increment it. Now we're going to iterate through all the counts in the hash table. Then we check if the count is odd. We take num characters modulo 2. This will return 0 if it's divisible by 2 evenly, or there's no leftover values. This means it's even. If num characters modulo 2 is not equal to 0, then we know it's odd. So we take our odd character count and increment it. If the odd character count is less than or equal to 1, so 0 or 1, then we know a permutation of this string can form a palindrome. If that's the case, this will return true. If it's greater than 1, then it can't form a palindrome, and this will return false. So now we return to the main function. If is permutation of palindrome is false, we'll simply skip it by. But if it's true, we need to add this string to the solution output. We take the string, convert it to an array, sort the characters from the string, and then rejoin it back into a string. By sorting it, we're able to group all the strings that have the same characters. This means they're permutations of each other. First, we check if the string exists in the hash table. If it doesn't exist in the hash table, then we initialize an empty array for this sorted string key. Then we just push the original unsorted string to this array. This is how we're going to track all the different strings that are permutations of each other. And finally, we return all the values from the Permutations of Palindromes hash table. So when we call object.values, it returns the values as an array. So it's going to be an array of arrays, which is exactly what we want the output to be. We run our code and the tests pass. So in this question, we really had a deep dive into both palindromes and permutations. We thought deeply about what it meant for a string to be a palindrome, and how we can form a palindrome from different permutations of strings. And then by sorting, we were able to group strings that are permutations of each other. Thanks everyone, and I'll see you in the next lesson.